Okay, so today we're going to be looking at the last section of the trigonometry unit, which is trigonometric identities. Now, what we're going to be doing today, the most confusing thing I think for students in this section is when you see your first question in a couple of minutes, it looks like an equation that you have to solve. And these are not equations. What trigonometric identities are puzzle pieces that you use to take a really complex equation or segment of an equation that has a bunch of trig stuff going on in it, and you want to reduce that section down into a much simpler version of itself. So all that we're going to be doing is practicing taking complex looking equations and making them look less complex, like the other side of the equal sign. Sometimes that requires you to actually manipulate both sides of the equal sign, but never ever are you going to be crossing over the equal sign like you would if you were solving an equation. So in other words, these are left side, right side proofs, but you need to know what the puzzle pieces are to be able to do those proofs. And these are some of the tools that you're going to require. Now, if you're in my class, which I'm just saying that because some people might be watching this stream later that aren't in my class, but if you're in my class, you would have received a handout with some of these trig identities, and these are the tools we're going to be using. So these are some of the puzzle pieces, in other words, that we're going to be using, okay? So we've already talked about the tan. Now, you can use x or you can use theta, and I'm going to use both. It doesn't matter which one you're using. The tan can be broken down into sine theta over cos theta, or sine theta over cos x, sine x over cos x. This is another identity, sine squared x plus cos squared x equals 1. This is another identity based off of this one. This is another identity based off of this one. I'm going to show that on the next slide. And these are what we call the secondary trig identities, or the reciprocal identities. So we know that the primary trig identities are sine theta, cos theta, and tan theta. But if you do 1 over sine theta, they renamed that fraction as something called cosecant theta, or cosecant x. Now, by the way, I absolutely cannot stand these things. The only reason, if I'm not mistaken, that these were created was to make typesetting in the past, when they used printing presses, easier, so they didn't have to write these fractional versions of the expressions. But almost every time you see a cosecant, a secant, or a cotangent, you have to rewrite them as 1 over sine, 1 over cos, and cos over sine anyway. So I find them to be a little bit wasteful with today's technology and the way it is, to have to learn them, but they still do exist, and some people still use them. So you do need to know what they look like. So anyway, this is, and I think I'm going to write this down so that you have the actual wording next to these. This is called cosecant. This is called secant. And this is called cotangent, which I'll just write as cotan. All right. And the way that I was taught to remember what word goes with which ratio, for every primary trig ratio, you have a co-trig ratio. So sine x, the reciprocal of sine x, is cosecant because it has to have a co-word to go with it. Cosine already has a co-word for it, so its reciprocal is secant, and tangent needs a co, so cotangent is tangent's reciprocal function. So just be careful how you wear your tool belt. Okay, so let's discuss some of these things. I would like to show you some of the proofs. Now, what is cosine squared? And just to show you that you can use theta, let's write theta instead of x here. What is cosine squared theta? That's just a fast way of writing this. Instead of writing cosine theta squared, they brought the 2 in beside the cosine instead, and we say cosine squared theta. So this is not a function notation thing. This is actually a power. So it's one of those weird exceptions that they've accepted throughout mathematics. All right. So the same thing with sine squared theta. That just means sine theta squared. It's just a short form of that. So how does cosine squared theta plus sine squared theta equal to 1? Well, if we go back to our circle trigonometry stuff that we were doing recently, that's a terrible circle. And this is pretend that this is not a radius 1 circle this time. So this radius is r. We know that cosine theta is equal to x over r. And we know that sine theta is equal to y over r. So let's replace these two things with those fractions. Let's substitute those fractions in. So remember that cosine squared theta just means cosine theta squared. So cosine theta is x over r. Sine theta squared is y over r. And what we're doing here is a left side, right side check. So we want to check to see, does that equal to 1? So how could we expand this? Well, what is x over r squared? Well, that's just x squared over r squared. And the other one is just y squared over r squared. And I'm going to pause there for a second and let that sink in, okay? So we took our trig ratios from our circle trigonometry, and remembering that cosine theta is equal to the adjacent over the hypotenuse, which is x over r on a Cartesian plane, and sine theta is equal to y over r on a Cartesian plane, we just replaced cosine squared theta with x over r squared and sine squared theta with y over r squared, and then we just squared both of those brackets. Now they already have a common denominator, so I can group the numerators up, right? But what does x squared plus y squared equal in our circle? Let me make that circle a little bit nicer. Chat, what does x squared plus y squared equal? That's correct. If you think about it, y is the red height here, x is the x length here. That's just two sides of a right angle triangle, which we used r to represent the hypotenuse for. So x squared plus y squared is just equal to r squared. Well, if that's true and we sub that back in here, we get r squared over r squared. Well, r squared over r squared is 1, and we've just proven the left side, right side. So one of our identities is cos squared theta plus sine squared theta is equal to 1, and now you have the proof that that is true. I'm wondering how many of you have seen these 3 letters written after a proof. I used to see this all the time in university, and at first I had no idea what it meant. Luckily, the teacher that first showed it to us did explain it to us. This is Latin for quat, and I hope I remember this properly, erat demonstratum. And if you know anything about Latin, Latin is very close to French. If you know any French, this is very similar to qui était à démontrer, which stands for which was to be demonstrated. And that is often, QED is often written after a proof to show that that is exactly what we were trying to demonstrate in our proof. And therefore, we are done the demonstration. Okay, so if you ever see QED in anything, that just stands for that Latin phrase. So this cos squared theta plus sine squared theta identity leads to two more, actually more than that. If I isolate cos squared theta, I get 1 minus sine squared theta. That is another identity. If I isolate sine squared theta, I get 1 minus cos squared theta. That is another identity. Remember, these are puzzle pieces, and I know you don't know what these are necessarily used for yet, some of you. These are puzzle pieces that we're going to use later on in complicated equations to try to make those equations simpler. So if you ever saw 1 minus sine squared theta in an equation, you could immediately change it to cos squared theta. Same thing with 1 minus cos squared theta. You could immediately change it to sine squared theta. Here's another one. I'm not even sure if this one's, I think this one's in your handout for those of you that are in my class. If I divide all of these by cos squared theta, sine squared theta divided by cos squared theta can be changed, since sine theta over cos theta is equal to tan theta, to tan squared theta. Cos squared theta over cos squared theta is 1. This becomes tan squared theta, and 1 over cos squared theta, since 1 over cos theta is equal to secant. I always forget how they write secant. Give me a second here. I learned all this stuff in French, so okay, it is sec theta. All right. So secant theta. Then this becomes secant squared theta. And that's another identity. If we took the original equation and divided everything by sine theta and sine squared theta instead, we'd end up with cotangent theta squared plus 1 is equal to cosecant squared theta. So there's a lot of things that you can do with this original equation here to create new identities that you can use to make things a lot simpler. So if we go back to this page temporarily, I want you to look at the center column here. I'm hoping from this first equation you can see where the sine squared x equation comes from. We just isolated sine squared x by moving the cos squared x over. And where the cos squared x identity comes from, we just brought the sine squared x over. And I showed a couple more from there as well. Okay, so let's actually look at an example of a trig identity. So I'm going to show you this one right now, and we're going to read through these useful techniques at the same time. Now, not all of the useful techniques will be in this particular example, but the main one is. When you look at an equation that is asking you to prove that one side equals the other, and everything is trigonometry, the first thing that I want you to think about is write everything in with respect to sine theta and cos theta, or sine x and cos x. Because those are your primary Legos, or puzzle pieces, if you will. All right? You have to write everything out in those terms before you start. Then sometimes you're going to have to factor, or you may have to expand. Then you're going to have to look at some of those tool belt patterns. And then you might have to find common denominators and stuff like that. We're going to see some more complicated examples in a second. However, I have to tell you folks, I cannot show you every possible example in today's lesson, and a lot of this has to be learned by just trying as many as you can and starting to see all the patterns that exist with these. So let's start with this one. It's actually a very, very easy one. I want you to notice that not everything is written in sine and cosine fashion, right? We have a tan x in there. So what identity can we use to help us get rid of tan x? Well, if I go back to my identities page, and if you have that handout that I gave you today, tan x is equal to sine x over cos x. So let's use those, or that Lego piece, that puzzle piece, to replace tan. And we're going to do a left side, right side check here. So tan theta, or tan x, is equal to sine x over cos x. Now, I want to pause here for a second. I'm going to finish the left-hand side here, and that is times cos x. So all we did was change the tan x, okay, to sine x over cos x. Sorry, I forgot to write the full equation there. Please be aware, this is what I meant by this looks like an equation, right? It looks like you're being asked to isolate x. That's not what you're doing here. You're trying to make this side be the same as this side. All right? So our right side is just sine x, and this is why we're doing a left side, right side check and dividing those two. You never cross over the equal sign. And the reason I'm saying this, folks, is because through my experience, I see students do that all the time. They'll take the sine x and bring it over here, make it equal to 0, and then they have no idea where to go from there. So don't do that, all right? This is not an equation. Anyway, so I took tan x, replaced it by sine x over cos x. This is times cos x. As you can see, this is an extremely easy proof because those two now cancel out. And we're left with sine x on this side and sine x on this side. And we've now proven that. So very, very simple one to start. That's the idea behind all of these. Let's move to the next one. So as you can see, very quickly, this can become something that looks a lot more complicated than what originally was thought, right? So, and now we're using the secondary trig ratios, cosecant. We can't use cosecant, so let's do our left side, right side here. So can you think of, and have you already perhaps memorized, what are we going to replace cosecant with? So remember that every co has another trig ratio that doesn't have a co in it. So cosecant can't go with cosine. Cotangent goes with tan. So what's the only one that goes with cosecant? It has to be the sine, but it's the reciprocal. So cosecant x is going to become 1 over sine x. And this is a case where we're going to change both sides. Sometimes you have to do that because you won't be able to tell if you don't change both sides when they become equal. All right? So oftentimes what we're trying to do is to take the more complex side and make it look like the less complex side, but sometimes both sides can be relatively complex. This one has a cosecant in it, and as we said above, one of the first things you should always do is convert everything into sine and cos. So we have to change that cosecant to 1 over sine x as well. Now that's pretty much as simple as it's going to get. On this side, what am I going to do next? Well, I'm going to distribute the 1 over sine x into the bracket. 1 over sine x times 1 is just 1 over sine x. And 1 over sine x, and I'm going to write this the long way. I'm sure some of you could probably simplify this quicker than this, but if I write it the long way, it would be sine x times 1 over sine x, top times top, bottom times bottom, right? Well, these two simplify. They're both the exact same thing, dividing each other to 1 over 1. And therefore, I have 1 over sine x plus 1. And if I rewrite that, which I technically don't have to do, but if I rewrite that in the same order as the other side, I now have the exact same thing on both sides. Okay? So the idea here is in an expression of some sort in the future, like grade 12, university, you're going to have this expression show up as one part of a big equation. And if you can rewrite that as 1 plus 1 over sine x, it'll be much easier to work with. So that's the idea of what we use identities for. We use identities to simplify expressions into more manageable pieces. Let's do another one. So from easy to mid-range to hard. So this one's going to be the hardest one. It's actually going to be the last one we do today as well. So left side, right side. Now I'm sure you can see which side is more complicated. So clearly this side is much more complicated than the other. But this side does have a secant in it. So we're going to take that right-hand side and we are going to get rid of the secant x. Remember that every secondary trig ratio has a co of some sort, right? So secant's co would be cosine. So it's 1 over cosine x. That's a multiplication. So we'd have 2 over cosine x as the simplified version of that side. And I'm going to pause there for a second. Take a look at what I did. We changed secant x into 1 over cosine x. That's multiplying 2. Top times top, bottom times bottom. And you're starting to see why you cannot be affected by your fraction rules anymore. Because your fraction rules are going to come into play in very complex scenarios like this one. You have to, without a shadow of a doubt, know how to add and subtract fractions, how to multiply fractions, how to divide fractions, because they show up in all these other types of scenarios. So I'm hoping everybody's okay with the right-hand side. Let's take a look at the left-hand side now. So I'm just going to write it out the way it is. Does anybody have any idea of where we have to go? What do we have to do to start working with that side? So just to help you out, let's go back up to some of the suggested processes we're supposed to follow when we do these. All right. So we made all of our trig functions look like sine and cos. Do we have to factor or expand? No. We did already look for our tool belt patterns. We haven't seen any others yet. But look at this last suggestion. Find common denominators in fractions. If I go back to this, do I have a common denominator yet? It's 1 plus sine x and 1 minus sine x. I do not have a common denominator yet. So remember when we were doing rationals and we were adding rationals? This is basically a rational that has trigonometric functions in it as well. So we have to find a common denominator to those two. Now, I didn't leave quite enough room here. Let me see if I can just move this part over. I can't. Well, I can now. I'll move all this over too. Come on. Okay, for some reason it's not letting me move it over. All right, I'll do it on a separate line then. Maybe I can fit it in. So I need to find a common denominator with those two. So if you remember your rational expressions, when we were finding common denominators, you basically look at the first denominator and you say, what does the second denominator have that the first denominator doesn't have? So the first denominator does not have a 1 minus sine x, so I have to multiply the top and the bottom by 1 minus sine x here. What does the second denominator have that the first what does the second denominator not have that the first denominator does have? Well, the second denominator doesn't have a 1 plus sine x, so I'm going to have to multiply the top by 1 plus sine x here. Okay. So what does that do? Well, that gives me cosine x times 1 minus sine x plus cosine x times 1 plus sine x, all divided by 1 plus sine x times 1 minus sine x. And I'll pause there for a second and see if there are any questions. Okay, I don't see any questions. I'm going to assume that everybody's okay. Does anybody see what we can do with these two brackets down here? What kind of a factored form is that? If I expand it, what kind of expression does it give me? That is a difference of squares. So my bottom, if you remember the pattern of a difference of squares, it's 1 squared minus sine squared x, or sine x squared, which we write as sine squared x. But 1 squared is just 1. Now, does that look familiar to you? I'll come back to that. What about the top? I have to distribute the cos x into both of those brackets. And this is very similar to stuff you would have been doing in your rational expressions section of the course. All right? So cosine x times 1 is just cosine x. And then we'll have minus cos x sine x plus cosine x times 1, which is just cosine x. And then it'll be plus cosine x sine x. And I'll pause there for a second. So are there any questions with what I did at the top there? Does anybody see what happens at the top of that fraction? What does this term and this term do to each other? Correct, chat. These two terms are the exact same, but one is a minus and one's a plus. They cancel out. What's left? You've got a cosine x left with another cosine x left. That's 2 cosine x's. Now, what does that bottom become? What's 1 minus sine squared x? If we go back way at the beginning, well, even this slide here, didn't I show you an identity for 1 minus sine squared x? One minus sine squared x, oops, sorry about that. 1 minus sine squared x just becomes cosine squared x. Now this is looking a lot more similar to that now. What happens when you have a cos x divided by a cos squared x? Well, what happens when you have an x divided by an x squared? 1x cancels out with 1x and you're left with 1 over x, right? Or if you have an a over a squared, you have the a's cancel out, so you have 1 at the top and 1a at the bottom. So what's going to happen with the 2 cos x's? The 2 cos x's are going to cancel out. One of them is going to get canceled out from the bottom. And we're left with 2 over cos x, which is exactly the same thing as what was on that side. So I'd kind of like to go over this one again and look at how complicated it was at the beginning, and we got it to look exactly like 2 over cos x. So imagine having all of this show up in an expression that you're working on in math, and you could reduce it to, I wouldn't write it as 2 secant x, I'd write it as 2 over cos x, but imagine reducing that. Like, how much work would you be saving yourself if you could do that? And that's what trig identities are all about. So what I want you to remember is we had a fractional problem here that we had to add them, and we couldn't do it because they didn't have common denominators. So as soon as we started finding a common denominator for those, then everything started to kind of fall into place because we were able to distribute the tops, which canceled out one of the uglier terms, and it also joined the 2 other terms and gave us the 2 that was missing from that side that we needed for the right-hand side. Right? This 2 popped up by doing that expansion. The bottom, you had to recognize as a difference of squares, even though it doesn't look like a traditional quadratic. And this is where your math skills are all starting to join together, requiring you to remember how does everything work, even if they don't look exactly the same as what we're used to. So 1 plus sine x, 1 minus sine x, that's a difference of squares. How does a difference of squares expand? Now, you could have used FOIL. If you would have used FOIL, you would have gotten the exact same thing. But then when you get to this step, it's like, wait a second. I know what that is. That's an identity. That's one of my puzzle pieces. And then you put that puzzle piece in and cancel stuff out, and you end up with what you were looking for on the other side. And that's trig identities. This can be one of the most fun sections of math once you get used to it, if you like puzzles, if you like to puzzle your way through things. Now, there's one thing in this series of steps that maybe should have been written in there. I stole this note from another teacher, so I didn't think about it till now. If things don't seem to be working, start over. You know what? I'm going to write that in, because that can happen. That sometimes you'll be working on a fairly complex proof that requires trig identities. You use one of the puzzle pieces, and it just happens that that will make things look uglier. And if you go back and start over and use another puzzle piece instead, it'll fall into place a lot faster. So if things don't seem to be working, you may have to start over, which is maybe one of the only things that's not as much fun in this section, is when you realize, oh no, nothing's working, I have to start over. But most of the time, it will work out slowly but surely as you start to follow these steps. Okay, and like I said, the most important one is changing everything into sine and cosine, and then see what you're given. Can you replace something with your tool belt patterns? Can you factor expand? Do you have to find a common denominator? I cannot show you an example of every type of these, folks. So I'm going to throw some questions at you. I actually have a handout. Instead of going to the book, I'm just going to give you a handout that has a bunch of these on them. And that's going to be your homework for tonight, is to try to work through those questions. And probably what we're going to be doing tomorrow is we're going to be correcting those questions together, especially the ones that you may have struggled with. because this does take a couple of days to start to sink in. And it's extremely important because it comes up all the time later on. But that is the end of today's lesson. I know it wasn't very long, but it's better to get you working on these as fast as possible. And you also have, I think the last question on your ISU is, not ISU, sorry, your culminating activity is going to have this as well. So I'm going to stop recording.